The system we selected is for the immune system control of HIV/AIDS. The system models the immune response to a drug designed to maintain the virus count at prescribed levels. The input, desired virus count change, is associated with the drug's prescribed levels. From there, it moves through our control system with its associated transfer function shown here and generates a virus count change in the body. This change is fed back through the system until the desired virus count change has been achieved. In evaluating our system stability, we found 3 poles and 1 zero. On our pole zero map, we can see that all the poles have a negative real part. This indicates our system is stable. Because our system is third order, many of the calculations we previously learned for second order systems do not apply. In order to remedy this, we decided to perform a dominant pole approximation where we assume that the slowest part of the system dominates the response, and the faster parts of the system can be ignored. The system must be stable in order to perform this approximation. We did this by evaluating which poles were closest to the origin, since those have the greatest effect on the response of our system. The imaginary part of the repeated root was removed, since it was further away from the origin than the real part. The resulting transfer function and pole zero map are shown here. After the dominant pole approximation, we now have a 0 on top of negative 0.02 and a pole on the bottom of negative 0.0199. Since these are approximately equal, it's safe to approximate the system by canceling the 2 out, and we are left with a reduced transfer function shown here. This is what the remainder of our open loop calculations will be based on. The Bode diagram shown to the right gives a comparison of the frequency response between our original and the reduced transfer function. Due to their similarity, this can be used as evidence for the effectiveness of our approach. Our system has a natural frequency of 0.2295 radians per second, 2 poles of negative 2.6419 and negative 0.0199, and no zeros. These are plotted on the pole zero map shown to the right. Here's a comparison of the unit step responses for our original versus reduced systems. The final settled value did turn out to be somewhat different, but this can be tuned with KP. The reduced system is decidedly overdamped due to its 2 real roots, and the immune system responds to the drug within a couple of minutes of administering it. Our system has a rise time of 110 seconds and a settling time of about 197 seconds. These were calculated from the step info function in MATLAB. There is 0% overshoot due to the overdamped system, and for the steady state error, we followed the formula 1 over 1 plus Kp, where Kp is found by taking the limit of g of s as s goes to 0. We found that the steady state error is about -1 times 10 to the -4th.
In order to find the required forms of the state space representations talked about on the next few slides, we first found the transfer function of our system as a closed loop system with the controller GCS set equal to 1. Due to the feedback loop shown in the diagram at the bottom of the slide, we were able to calculate the closed loop transfer function.
On this slide, we see the cascade form of our closed loop system described above, where we see our transfer function here from the closed loop system, and it being factored into our appropriate poles here. Then using those poles and the block diagram method shown in class, we're able to find our state space equations, where x1 equals c of t, x1 dot equals negative 24.17 times x1 plus x2, and x2 dot equals 21.51 times x1 minus 520 times the input r of t. Then you can see from these state space equations, we're easily able to get our state space representation, where you can see in our A matrix, we have our poles across the diagonal, negative 24.17 and 21.51, as well as our B and C matrix, making up the entire state space representation. Below that, you can see the signal flow graph, which provides a good visual representation of the system and allows us to easily follow what exactly the input goes through in order to get to our output. On this slide, we see the parallel form of the closed loop system, where we have our closed loop transfer function here that's again factored. Then using partial fraction expansion, we're able to pull out that equation into its 2 separate poles and find the appropriate constants above it. Then using these values, we're able to find the state space equations where c of t equals x1 plus x2, x1 dot equals negative 24.17 times x1 plus 11.38 times rt, and x2 dot is equal to 21.51 times x2 minus 11.38 times r of t. Then using our state space equations, we're able to get our state space representation, including our A matrix, where we again see our poles along the diagonal. We also have our B matrix and our C matrix, and you'll notice a big difference between this form and the cascade form in that both x1 and x2 are involved in finding y, our output. Then, using the state space representation, we're able to find our signal flow graph, which gives us a pretty good representation visually of what our system kind of goes through from input to output.
To find the controller canonical form of the closed-loop system, we derive the state space equations from the transfer function. We set state x1 equal to c of t, and the derivative of state x1, or x1 dot, to be x2. Since our transfer function is a second-order system, we then simplified the derivative of state x2, or x2 dot, to be in terms of x1 and x2 by isolating the s squared term. The state space representation is shown at the bottom in controller canonical or phase variable form. An important property of the controller canonical and observer canonical forms is that they are duals of each other. The first section of the slide derives the controller canonical form and companion form. The companion form was used to check our work when finding the controller canonical form and observer canonical form, as one of the relationships between the two is that the A matrix of the observer canonical form is the transpose of that of the controller canonical A matrix in companion form. At the bottom is the flow diagram of the closed-loop system in controller canonical or phase variable form. To find the observer canonical form, we first multiplied the transfer function by 1 over s squared over 1 over s squared. We then simplified the altered transfer function as shown by the second half of the slide. We set c of s equal to x1. We then broke up and simplified the equation into separate states as shown. We then found the state space equations by setting y equal to the state x1. Based on the equations found on the previous slide, we found the rest of the state space equations as shown. We then found the state space representation in observer canonical form and drew the flow diagram based on the state equations.
This is the beginning of section 3. The following block diagram represents the closed-loop system where g of s is the original transfer function and gc of s is some constant kp. That constant kp will be adjusted to achieve a 50% improvement in both rise time and settling time. Kp was found by setting kp equal to a range of values that it could possibly be and then looping through them, calculating the rise time and settling time for each one of these. When the rise time and settling time were at approximately a 50% improvement, that value was chosen. That value happened to be kp is equal to negative 0.0001. The state space representation for our output system was found by converting the block diagram into a transfer function and then extrapolating the states from that. x1 was said to be the output, y, or c of s. x2 is the derivative of x1, x1 dot, and x2 is negative 0.1047x1 minus 2.662x2 plus 0.052r, the input, which yields the following phase variable representation as seen below. The transfer function was then calculated from that phase variable with c times the inverse of is minus a, where I is an identity matrix, a 2 by 2 in this case, b plus d. The inverse of is minus a was calculated by doing the adjoint over the determinant, the intermediary step shown there, resulting in the transfer function of the closed loop system being 0.052 over s squared plus 2.66s plus 0.1047. The eigenvalues are the poles of the closed loop transfer function, or when the determinant of is minus a is equal to 0. This results in the eigenvalues of negative 2.6219 and negative 0.04. The eigenvectors are when some vector multiplied by the A matrix is a scalar transformation of that vector. This is shown by the following equations. When these equations are solved by solving a systems of equations, it results in x1 and x2 as shown below. The state transition matrix can be calculated in a variety of ways. Here it was calculated by taking the inverse Laplace transform of the inverse of is minus a. This results in the following state transition matrix, and it was calculated using the following commands in MATLAB.
The state variable solutions for a second-order system with an input of u of t or the step function can be broken up into two parts, x1 of t and x2 of t. x1 of t is equal to the output response with a unit step input, and x2 of t is simply equal to the derivative of x1 or the derivative of the output response. The output response with the step function input can be calculated by taking the transfer function and multiplying it to the step function input 1 over s. After this multiplication is done, you take the partial fraction expansion, and after this expansion you take the inverse Laplace transform to get the output response, y of t, within the time domain. These graphs represent the state variable plots x1 and x2 given a unit step input. x1 is the graph on the left, and x2 is the graph on the right. The output plot of a tuned closed system is the graphical representation of the output response, y of t, in this case, given the input of a step function, u of t.
To complete the next section, we went back to the open loop transfer function as found at the beginning of the presentation. To determine if our open loop system was controllable, we put our transfer function into controller canonical state space representation. We followed the same procedure as in section 2 when we found the controller canonical form of the closed loop system. By finding the determinant of the controllability matrix to be a non-zero value, we determined that the controllability matrix is full rank, which means that it is invertible. The system is therefore controllable.
We're going to take a look at the open loop state space and observer canonical form in order to determine the observability of our system. Here we see the observer canonical state space representation based on our open loop transfer function. From this, we can derive our observability matrix shown here. Then we can see the determinant of the observability matrix is equal to 1, not 0. And as a second rank matrix, this means our matrix is full rank and invertible. As such, our system is indeed observable.
The state feedback controller enables the poles of any given transfer function to be moved, assuming that the system is controllable. This is achieved by multiplying feedback to a constant K matrix. The values of this K matrix can be found by taking the matrix A minus BK and setting it equal to the state matrix derived from the desired poles. The values of the K matrix can then be found. In our example, 1 is negative 0.003745, and K2 is equal to negative 0.00065. With these values, a new transfer function can be created. In our case, the top remains the same at negative 520, but the bottom now represents the two poles moved to negative 1 and negative 2. The movement of these poles enables many different changes, such as changing rise time and settling time compared to the original system. The design of the controller can be seen through this diagram. After integration, the x is multiplied by the negative k matrix and fed back into the input of the system.
To design a state feedback observer based on the added poles at negative 10 and negative 20, we first found the desired transfer function of the new system and put it into observer canonical state space representation. We then set the A matrix of the new system equal to the matrix A minus LC found using the current system with unknown values of L1 and L2. By setting the two matrices equal to each other, we found the values of L1 and L2. The added poles give the system a lower rise and settling time than the original system. Based on the values of L1 and L2 found on the previous slide, we designed the observer as shown.